Welcome, everyone. Thank you for joining us for today's GoAERO Prize Expert Lecture. Uh, I'm happy to introduce Gwen Leiter, our GoAERO CEO. Gwen, I'll turn it over to you to introduce our amazing lecturers for today.
Thank you, Rebecca. And we are thrilled today to bring you both Ramy Mourad and Mark Page in this expert lecture. As you all know, GoAERO is supported by the most wonderful aviation and first response companies in the world, including Boeing and RTX and Honeywell, along with many of our other supporters. And we are also joined by over 35 different organizational partners around the world. And we all collaborate to bring you the programming and these expert lectures, as well as the competition. So thank you so much for all of you for joining us today. I am thrilled to introduce two colleagues and friends. This will be an incredibly exciting lecture for you all on how to actually build something that is safe and amazing technology within a 3-year period. First, we have Ramy Mourad, who is Director of Engineering and Urban Air Mobility at Boeing. Ramy has held this position since October 2021. And with nearly 2 decades of dedication to advancing commercial and defense aerospace, his career truly is a testament to leadership and innovation and transformative impact. In his current role, Ramy heads up Boeing's UAM engineering collaborations with industry leaders such as Wisk, Aero, who you've heard from as well, and SkyGrid. And with Boeing affiliates, his team is actively designing and building one of the world's first certified commercial autonomous electric aircraft. By leveraging Boeing's scale and strategic capabilities and the Wisk Silicon Valley innovation and agility, he really models strategic foresight in the growth of the UAM engineering team. As an aviation enthusiast and pilot, Ramy's journey includes pivotal roles at a Honda Aircraft Company and Eclipse Aviation Corporation, which you will hear about. And Ramy truly believes that the aerospace industry is on the cusp of a technological revolution, making aerial travel available to a majority of civilization. And he strives every day to foster diverse, collaborative, and innovative team cultures in pursuit of that future. And with Ramy, we have his former colleague and current friend, Mark Page, who is the founder and CTO of JetZero. So Mark worked for 18 years at McDonnell Douglas Boeing on transport programs, including the NASA prop plan and NASA-sponsored blended wing bodies, which he co-invented. Frankly, he was the first one to talk about any of this. Mark Page has became the youngest technical fellow at McDonnell Douglas for his work on the blended wing body. In the year 2000, Mark moved to Swift Engineering as chief scientist, where he led the aero design of several race cars that enjoyed successful racing careers, including NASCAR Cup racers. And then in 2007, Mark designed the Eclipse concept for Eclipse Aviation, and we will hear about that today. And this concept went from contract to first flight in just 200 days. In 2012, Mark co-founded Design Technologies with 4 colleagues that specialize in vehicle development from design to flight. To date, Design has taken a new airplane to flight every single year of its existence, ranging in weight from 3 pounds to 1,500 pounds. He led the design of the Mooney International M10 Sport Trainer and Beta's Aliyah, which we all know about. All of these aircraft were taken to flight, and the Aliyah 250 is now in flight, is now the in-flight test leader and a leader in the eVTOL industry. In early 2021, Mark founded JetZero to deploy blended wings technology for a zero carbon future. JetZero and NASA are developing new technologies that increase the blended wing body fuel advantage when compared to present airline fleet. And the fuel savings is apparently 65%. So JetZero's blended wing body incorporates features that are able to enable the earliest possible adoption of hydrogen. So you clearly have two phenomenal experts to hear from today. They are experts in a whole host of different technologies, and they are also experts in building quickly, productively, and well. So without further ado, I will turn this over to my two friends and our experts, Ramy and Mark.
Thanks, Gwen. What an awesome intro. A couple thoughts on GoAERO. I think there are so many parallels with the opportunity of participating in GoAERO and the story that Mark and I have the privilege of telling you all today. So I just want to commend Gwen, you and the GoAERO team on providing a potentially life-changing opportunity through this competition for many on the call here. Similar to how this impacted my life. I was only, this was, geez, 17 years ago. I was in my early 20s when, when we had a chance to do this. And it was an opportunity to work with legends, the story we're about to tell you. So for me, early 20s something, just coming off of the Eclipse 500 certification program, huge learning experience, I had a chance to work with Mark Page, who I looked up to like a legend in the industry already. And that was 17 years ago, Mark, can you believe it? And we got to work with other legends like Oliver Macefield and Terry Tomini and some phenomenal folks over at Eclipse doing great things, and your team at Swift Engineering at the time. I actually, Mark, remember your passion for blended wing body, just talking about it over beer.
Yes.
Back then. But I don't know if you wanted to say a word or two, just maybe do you remember how, Mark, you were tapped for the project we're about to talk about?
So yeah, the preamble would be that I was working at McDonnell Douglas Aircraft Company straight out of college in the aero department. And the aero department was exceptional, just amazing people who are now CEOs and chief science officers in that little aero group. It's amazing where they've all gone. But in 1997, we merged with Boeing. And that's why I took a sudden left turn into race cars, open wheel race cars, dragsters, and cup cars. It was a total blast. At the time, I could tell that the opportunities for blended wing would come faster outside of Boeing at that time. But Boeing continued to do amazing research on the airplane. It has a huge bank of knowledge on the concept and really pioneered the actual creation of something that was akin to a product platform that you could develop from. So yeah, did that sort of stuff, and then got into the companies that were mentioned by Gwen, and each one of them presented fun opportunities. So I was doing race cars at Swift, and we had a slow time. We had a new president who wanted to build landing gear doors for 737 and never design a new race car or airplane again. So we were waiting. There was no business. When we made that decision, there was no business. So I said, hey, could I take the leftover carbon composite materials, and some of these guys were just sitting here twiddling their thumbs, and some of the engineers, and maybe a couple $100 to go buy some radar control stuff, and let's see what these guys can do with their master's experience on race cars in the UAV world. So we did the Killer Bee blended wing body UAV, and that took off and became the Raytheon Killer Bee, and then the Northrop Bat. So lots of fun. But with no further ado, I need to let Ramy.
Well, you know, so the context here, by the way, fun fact, I actually got into aviation through studying aerodynamics for race cars. My first passion coming out of high school into college, I decided to study aerodynamics for cars. And it was during school that I fell in love with airplanes and ended up getting my internship at Eclipse. Now, back in 2004, 2005 timeframe, this startup company called Eclipse Aviation out of Albuquerque, New Mexico, was doing a very similar idea, but in a little bit of a longer range to this whole air taxi concept that a lot of us are talking about today from an electrification perspective. Back then, Eclipse was envisioning disrupting the whole hub and spoke model by providing small jets, very small jets. In fact, they coined the term very light jet, VLJ, where you have this 4 or 5 passenger little jet that could be short, require a short runway. And you can place them at regional airports nearby, and you could just kind of do this air taxi service where for the price of like a first class ticket, you could basically charter small jets to anywhere in the country. It's a pretty significant range. So over 1,000-mile range, and that was the idea, and it really captured the imagination of many, and attracted some tremendous talent at Eclipse. So some context for this story. Fast forward several years into Eclipse's journey, and we certified got the type certification for the first Eclipse 500. And just got into production system mode. In parallel, our CEO and COO and chief engineer were starting to think about what would be next. What would Eclipse do next? A bigger airplane, a smaller airplane, and started toying around with some concepts. So I actually remember getting tapped on the shoulder for this project, and it started with, "Hey, Ramy, can you be away for a while and that be okay? Can you like try, because we're going to do something a little bit proprietary. It's going to be a really small team and the timeline is intense. You're all going to have to be co-located in this place. Are you able to do that personally? Just disappear for a while." And I was like, oh my God, if somebody asks you that, the answer is hell yes. No.
For
So
sure.
I was smart enough to know that at the time. And like, so this story is one of those situations you get in life where you realize at the time that it's a once in a lifetime opportunity. And so I get to Wallops Island, Virginia, where we did this work, and meet Mark Page, Casper Vandershoot, several other phenomenal people. And we designed, built, and tested this concept jet in 7 months. And so the point of this story, we'll tell it at the end again, and you'll see it throughout, is that if you get the right people together and put the right focus on a project that is really, really ambitious, many might consider impossible. Yeah. It is absolutely possible. And it's a ton of fun along the way. We created a safe and very compelling concept with a very small team in a short amount of time with not a lot of money. And it was a highlight of my career, one of the most fun experiences I've ever had, genuinely. So let's jump into it. From concept to Oshkosh in 226 days. The story of the Eclipse concept jet. All right, so I talked a little bit about this, kind of set the stage for the Eclipse 500 timeline. April 2007 was the production certificate. 2006 September was the type certificate. So we started this project. I don't know, Mark, I don't know if you remember, you can tell a story of being tapped, but we started in January, I think it was December, January, is at the Christmas party, when Vern and the CEO of Eclipse and a few kind of had the idea of doing the next thing. This was December of 2006 timeframe, and you must have been tapped right around that time.
Absolutely, yes. And if you remember, the thesis was that it takes a long time to become a jet pilot. Why? Because you got to get your multi-engine rating first. And you look around, there aren't any single engine jets until the Vision SF-50 showed up. and we were all in that same stew trying to make the next cool airplane. So yeah, that was exciting. And I was actually pulled in to the discussion because I had been there. And Ramy, I don't think we met at this time, but
Nope.
I had been invited to do a review of the aerodynamic development and processes used on the airplane. And I had the chance to put thousands of little blue oil dots all over the airplane. And the guys flew it, and we landed, and we diagnosed some areas that could use some help. And the airplane was fabulous. And then Vern Rayburn says, Mark, so what do you do with this race car company besides that stuff? And I said, well, we gave a presentation. We showed delivering 40 open wheel race cars, all crated up, delivered to every race team in a spec series on the same day. And then everyone at the table from Eclipse leaned back and started whispering to each other. And Vern says, could you do a single engine jet by Oshkosh? And our answer was, we have to find a way to say yes. Take it away, Ramy.
Yeah, that's an easy hell yes. I actually remember those flight tests, Mark, when we were doing on the 500.
Right.
And I just now recall that it was you. I didn't even connect the
Put the
dots.
connection together, yeah.
Yeah, I remember it because I was at the time, my role at Eclipse was I was a flight test engineer, like just doing basic performance, stability, and control. And it was on our performance stability control aircraft that we put a whole bunch of those oil dots. And I remember asking, I think it must have been you. I remember asking, how does this even work? How is this oil not just going to fly? We saw the trace. I remember that. Cool. So we get to the next concept, and here's the kind of the genesis of the idea. As Vern and Mark and others started thinking about what would this concept look like and what would it need to be, and the idea was, how could we get to from a 6-person aircraft, 4 or 5 passengers, down to a 4-person aircraft with 2 or 3 passengers, and really make it super simple to fly, still have very impressive flight performance, still fly over the weather, but the concept had to be validated. So that we took really an automotive style approach to this concept validation strategy, with a highly confidential proprietary program on the side, not to distract Eclipse, the broader company, from what was a pretty challenging time. Anyone that's been through transition of type certificate, you just certified your aircraft, and you kind of have that, oh my God, now it's time to like deliver a lot of airplanes, because our backlog at the time was like 2,700 airplanes. So getting that whole machine up and running was a tremendous challenge. So we didn't want to distract the company, but we would use a small program to evaluate at Oshkosh a market reaction. Would this be the right next thing for Eclipse? So that was kind of the mission. That was a driver for this whole idea, to design and build something. So these were some of the very initial concepts that we came up with. Oh, one thing that is super important for I kind of touch on these already, for the concept. It had to be sexy. It wasn't just about the performance and being practical, but it had to look freaking good. And I don't know if you agree with me, but I think it does. So hey, Mark, maybe you can talk a little bit about how these players came about. Obviously, Eclipse was at the tip of the spear here, but you talked about how Swift got involved because of the performance. How do we pull in Basis, and what was their role?
Yeah, so Basis, they were based in Onondaga, Virginia, which is very near Wallops Field. It's a NASA and military facility where they launch rockets on one end of the facility, and NASA and the Navy have an airfield on the other side of the island. But Basis Technologies was based there. And why did we have them involved? They're a supplemental site type certificate shop, an STC shop. They take airplanes and make them into something a little bit different. So they know how to certify stuff. They know how to comply with all the practices you need to build a an aircraft that's going to be flown by people for real. And they were recommended to us by a company called it was International Aero in Long Beach, and they were going to do the paint job. And they said, well, you need to talk to bases. And we got involved with bases, and it was a total fabulous fun out there. And the year that when we were putting the airplane together was where they had this multi-week giant summer festival. Remember all the ice cream shops all lined up? So you'd go outside and there'd be Ferris wheels going. You'd go to all the different
Mr.
ice cream
Whippies.
shops. Yeah, it was a heck of a lot of fun.
Heck yeah. So basis was basically final assembly and test. And do you remember what we called the space they made for us?
No, what?
We called it Area 52. So we wanted to keep this place kind of secret. So on Wallops NASA flight facility, Wallops Island, Virginia, we put up like 20-foot plywood walls in this hangar to keep it, protected from looky-loos at bases. I remember that. It was super fun. Okay, so here's the mission. We go from December, from a Christmas party idea to Oshkosh in July, and I assume this audience is well aware of the mecca of general aviation air shows, that is Oshkosh. So we had our work cut out for us. So here's the parallels to GoAERO. What you will be doing, you will be building a timetable that looks similar to this as you build your aircraft and you design your aircraft. And what you're going to notice about this timetable is it would be wonderful if everything could work in series and you do step A and then step B and then step C just in a nice serial fashion. But the reality is when you're tight, you're going to have to think about what can be done, what can be validated early, and overlap certain parts of the design. So you're going to start to see that. Look how fast we went from the idea to a preliminary design review, which means a preliminary design review is an important part of engineering maturation. That's where you lock down your major system interfaces. So you basically say the interfaces are locked. I can get to detailed design with confidence on all the detailed systems. So Mark is the brilliant mastermind behind at the time it was called Swift Sizer. I think this has evolved several generations since, but maybe you can talk a little bit about what does this thing actually do and why was it first up?
So this is, you could probably tell, those of you who've seen this type of stuff before, it's an Excel tool. That's an airplane sizing tool that lets me try all kinds of alternatives for rigging the engine, balancing the airplane, estimating the stability and control, so I know where the fuselage has to go, so the aerodynamic limits line up, and capture the center of gravity vector with fuel burn off and different payloads and all that stuff. And because it's this kind of visual environment, it's not an optimizer I turn on and let run 40,000 solutions overnight. You really guide it. You look at stuff and learn why something is bugging the solution, making it problematic. And often letting the computer run longer is not the answer. You have to change something. You have to add a feature that your model of the airplane doesn't have at the moment. So this has been, I've used this on the BAT, the Killer Bee, on our airplane now, believe it or not, on the much bigger version now for the JetZero Z4. So
yeah, this is where like our high level requirements help us configure the aircraft. And what's the wing sizing? What's the distance between the wing and the tail, and the engine placement? Longitudinally. And so we ended up with the design basically showing I made this presentation a long time ago, and I was pretty excited about PowerPoint animations at the time. I have a very different approach to PowerPoint these days. But so we got this V-tail mounted behind a single engine, and we wanted to keep it simple with a single engine. So we had to figure out how do we deconflict the exhaust, from the engine and the tail. How do we make sure that in a rotor burst situation we're isolated from fuel tanks? And we'll show you some mitigations on how we mitigated a rotor burst situation and flight control cables. We actually needed to do a lot of work and wind tunnel testing, CFD, and so forth on the wake ahead of the inlet to ensure that inlet distortion is properly managed. So that shaped the spine of the aircraft and kind of helped us decide the width of the aft fuselage from a structural perspective. So this is the rotor burst thing I was telling you about. Mark, I think your team was were the masterminds behind this. Can you kind of share what are we looking at here?
Yeah. So what you're looking at, start with the image on the right. You're at the tail, very end of the airplane. The two blades you see going up left and right, those are the spar attach mounts for the left and right rudder vaders on the airplane. The tail cone itself has been taken off. You can see some bulkheads inside. And in this area of that aft fuselage part, all the controls are going to get to the pair of rudders on the back of the airplane who provide yaw control and pitch control, as all VTALs do. And the red block is the envelope of how the FAA defines a failure of a rotor disc. You take a third of a rotor, you blow it up, you release it, you spin, tumble it, and it fills that box when you smooth out the edges. And you want to swing that box around the axis of the engine because the chunk could go anywhere. And you want to make sure that under no circumstance are all of the controls cut to the tail. So we had redundant cables left and right, and you can see them at the bottom. You can see how we spread them so that possibility of an engine rotor burst would never take out all the flight control. You would always still have flight control, even with a complete explosion of the engine.
Very cool. A very important piece of early design, because if we thought about this later, it would require massive redesign. So this is an early flight control, safety critical flight systems in the early conceptual design, early preliminary design is absolutely critical. So, and then here's a really neat piece of engineering, very elegant in my opinion, how a rudder vader actually works, where you want to have a directional control in addition to the elevator. So I don't know, Mark, if you add anything you wanted to add to that mini animation there.
The funny thing is, in the middle, we didn't know what to call that thing. We just, hey, it's a standing man. It's the orange standing man. And his head gets pushed down when the airplane wants to pull up. And when he leans back, that's pushing the airplane nose down. And then you see just behind him, you can see the two sectors linked across the middle. And that, of course, is what the rudder command comes in on. And it plays a role in mechanically summing. This is called a summing link, summing the rudder and elevator inputs. So if I want to do a pure pull-up, maybe both elevators come up 10 degrees, same direction. If I want to do a yaw, I might have one up at 10 degrees, the opposite one at minus 10 degrees. And I can mix everything in between, and it actually makes exactly the same sense of an airplane for the pilot as a dedicated rudder and a dedicated elevator.
And I'll tell you, as someone who had the privilege of getting several flight hours on the airplane, it felt so good. Like you'd think maybe there's friction in the system. It felt so good and so natural. It was really, really well designed. Okay, so aerodynamic and structural design. So notice the bar here takes us from very, very first day all the way through CDR. These aero and structural designs are obviously highly coupled as you make changes to optimize aerodynamic performance and efficiency. You have to make sure that the aircraft is structurally able to do that. So we used computational fluid dynamics. These are a lot of I think the Swift tools here that Mark you guys had a chance to use. I love the smoke.
Yeah, definitely.
It's just so cool. Any thoughts on the initial CFD work?
So the thing that probably isn't apparent on the schedule, and you made a comment on that, Ramy, to do the airplane that fast, we had to parallelize things that would normally done in series. So everything had to be parallel. So the one thing that had to be released immediately, and I had Christmas vacation, we were already under contract, and then I had, it was 3 weeks later, we released the outer mold line for the fuselage, tailplane, and nacelles. They were all done, designed. We did all of our CFD because we had to. And if it wasn't quite awesome, well, we'll do a wind tunnel test later, maybe fix some things. So that was essential. If you, for example, those of you making any vehicle, outer mold line tooling, OML, outer mold line, the surface, the thing that's on the outside. If you can make all the tools for the making an airplane of the right shape, the outer mold line, you don't have to know what the structure looks like yet. You can make a tool. Everyone can be making that tool that you're going to mold it in. You get people started right away on a big, heavy project. And then your engineers are also figuring out how deep the spar is going to be, how thick the spar is going to be. But we picked a thickness for the skins that was good enough. And then the guys and gals could populate that with spars, ribs, and everything else months later.
Great point. Let's get past this one. So here's some more analyses that we had to do to ensure all the various flight configurations and flight envelope are explored in CFD before actual tests. So we have a good sense of how the aircraft will behave in high angle of attack or a high side slip. And like Mark said, that outer mold line was designed and pretty much locked in within weeks. Then we had to figure out the structure to make it all work. So this is a really fun animation here. Pay close attention to what's disappearing and then what's built back up. It started as the Eclipse 500. And so we wanted to use as much as we could from the Eclipse 500, but not much was left. We basically ended up with the wings, the nose, and the avionics, and the Pratt & Whitney engine. And the rest was designed up from that to rebuild it into this aircraft.
And that was a huge element of success because all of the systems that were plugged in this airplane had already been tested for compatibility, were fully certified. We knew that there was nothing that was going to happen with voltage mismatch, nothing was going to happen with bad grounding. Everything the first time we turned it on, it worked perfectly.
Yeah, that is a really important point to take here is we're one, if you want to go fast, where one could reuse in a modular way proven technologies, the hard stuff, avionics, actuators, engines, where you can not reinvent the wheel. You can make progress quickly. So here's where we got to just kind of borrow known components from the Eclipse 500. But this was all new structure here. So this is where we focused our energy. And yeah, go ahead, Mark.
I was just going to say that you can see the cockpit and passenger area kind of in gold. So that was, believe it or not, fiberglass. The tail cone was carbon. The reason the cabin was fiberglass was we were going to mate it directly to the aluminum nose gear barrel. And so the coefficient of thermal expansion difference between the materials was reconciled by using glass on the forward part and then really high performance carbon on the aft part. And of course, in manufacturing, you can make it all carbon, but that was an interesting element. And the other thing I'll say about the stuff you're about to see, we did all the structural design. We did our own structural analysis. We had an independent company take the same finite element model and do an independent analysis. And we only changed one thing, and it was one little link right there in the engine mount. That's the only thing we changed after all that work.
Yeah, Mark, a thought came to mind here. So weight is always a challenge when you're trying to defy gravity,
Mhm.
and airplanes get to do that. We ideally, this airplane design was conceptually much less than the prototype we built. Can you describe why and the whole concept around the safety factors on the first prototype and so forth? What thought process you and the engineering team had to go through to ensure that the first airplane works?
Right. So we were working with Oliver Maysfield from Eclipse, and as Ramy said, it was a secret program, so we got to talk to him and the chief parts guy, and then only two other people knew about the project at Eclipse. So we stole parts from that one person who knew that we were doing the game, and that's how we got the innards and started designing around those. But these structures, obviously, if you're familiar with composites, you know that the specific strength, how many pound or hundreds or thousands of pounds can a aluminum bar take compared to a carbon bar of the same shape. And so the carbon has much higher properties, especially in stiffness. So you can make it lighter. You could, whatever you have to do in aluminum, you could make it 2/3 the thickness or sometimes half the thickness. That was key. And it's very easy to manufacture. And so here you're seeing, this is a barrel of the fuselage. You're looking, the back end, I think, is this is a kind of a slice through the wing crossover. And with finite element models, you can see lots of little tetrahedra, lots of little triangles. Mathematically, you make each one of those a spring, and you push on the airplane with the load you think you're going to get, and you see how much stretches too much, and you make that thicker.
What was your safety factor that as you're designing this?
Right. So traditional aerospace is 1.5 safety factor, so 50% more strength than you need. And you also have specific maneuvers that are also beyond what any pilot would do normally. So we have 2.5 G. Actually, this airplane, I forget, it was actually 4.5 Gs
Mhm.
and 1.5 safety factor, which I think we bumped to 1.8, if I remember right.
Yep.
Just so we could be less perfect and get it done faster.
Yep. Yeah, I think in some cases we went up at two or and
Mhm.
even a little higher than two, just to where we were a little concerned. We would just bump up the safety factor so we wouldn't have to iterate on that design. We had no time to do that. So
Correct.
the airplane ended up heavier.
Yep.
But the purpose, the mission of showing the concept to the public, demonstrating flight, we still achieved. So we just had to make some trades when it came to flight test, a little longer runway than the ideal airplane would be, so would need, and so forth. But that was some of the stuff we had to do from an engineering trade perspective to make sure we hit the mission on time.
Mhm.
We're going to speed it up a little bit here, Mark, because I'm just looking at time. So I'm
Yep.
going to go a bit faster. Really, really fun stuff with wind tunnel work, where we're basically now validating the CFD with the wind tunnel models, and some of this stuff gets really, really intricate. So you can see the engine here with the inlet distortion rakes. They serve, these are tiny, tiny little, basically pitot probes here that are measuring the different pressures all around the inlet to help us make sure that the upstream shape of the aircraft in the various attitudes wouldn't starve the engine from air and the air that it needed to operate properly. So that level of precision was done in safety critical areas. Anything you want to add here, Mark, on the wind tunnel?
No, you keep going, man. That's it. You did good.
All right, cool. Oh, this was really cool. Why don't you take this one, Mark? So I'm going to overlay the CFD on this.
So
These are your oil dots.
These are the oil dots we were talking about. You put these dots of oil with a pigment on, you walk away, you fire up the tunnel or fly the airplane. You make the goo so it doesn't start moving until you get above a certain speed. And then it's like having a Polaroid of tufts on the airplane. It's showing you where all the air is going and where there's mischief. And if you look at just in front of the engine and below, you can see, wow, there's a lot of deflection there. Those streamlines are being pushed out, and there was a little vortex there. And we cleaned that up during this test. but it takes us in the direction of understanding where we have trouble. Look at the bottom, the bluish thing near the bottom. That's the fillet between the wing and the fuselage. The airplane, the pilot would be looking to your left. You can see the V-tails to the right. And that piece is really important because it can easily be, it's hard to keep that attached flow. That's hard to keep from stalling, making the flow go crazy. So if you look at the dots, some of the dots aren't moving, but all the dots that are moving are going aft. That's okay. If it slows down really great, that's okay. But if the dots go upstream, that means you have a massive separation vortex there, and you have an instant recognition of a problem area. So we were pretty pleased with this because it was just on the edge of stalling, but didn't.
This is one of my favorite learnings on this program, and so a testament to CFD work. And now, nearly 20 years later, CFD work is much higher precision. But you could see basically what happened in the oil dots was predicted and validated with the wind tunnel testing. That's where that type of testing really helps us. All right, so now we build the airplane, and look at when we started building. So Mark mentioned building tooling for the outer mold line ASAP. And we literally started building the airplane well in advance of CDR, well in advance, critical design review, where that's where you lock down basically your detailed design. So this is a slideshow, Mark. Why don't you voice over the slideshow just real super fast?
You bet. So you can see the autoclave. That's that big cavity there that gets pressurizes and cooks all the parts. Here's the aft barrel of the fuselage. You can see some white splotching on there. We were about to deliver it because we had some little imperfections in the carbon because we didn't need the best quality stuff. And the guys were just going to send it with little wrinkles. I said, no, you're not. So they cut it up and filled it and made it flush, but it looked so bad, people were scared. But here you're looking forward in the airplane, this fiberglass part of the airplane. You can see there's some foam in the kind of yellowish areas. Those are foam blocks so that you have a layer of cloth inboard, a layer of cloth on the outer side. Together they make a type of an I-beam and really stiffens the structure.
All right, so we started building the stuff in mid-January, and we start assembling in early March. CDR is at the end of March.
This thing that's interesting is that the end of February, everything was actually already built. So it was ready for assembly. So 3 months into the program, all the parts had been made.
Here's Area 52.
Mm-hmm. And these folks were so skilled, so capable, and they really loved working on the carbon and the aluminum parts of the airplane. They thought it was fantastic. They were always told that's really hard. Well, you heard about the weight issue we had on this thing. We had factor safety of 12 in some of those things. I had a little talk with my structures guy afterwards, but we ended up building it, overbuilding it. And so those guys could drill right through it. Shoot, they could screw into it. In the real world, you could never do that. It'd be much thinner.
Yes, that was one of the benefits of designing. And here's now we make it pretty, So we had done a little bit of testing before we started painting, just in case, and we'll show you pictures of that in a minute. But here's how the airplane basically came together, and a quick 360 around.
This is me in my rental car, holding my
that's right, hanging out the window with the camera,
one hand on the wheel. Yeah,
I love it.
Orbit.
Yeah, our team at the time was probably, actively there, about 20 people, 20, 25 people.
Yeah.
Building, designing, all the things. All right, so we start testing. First flight readiness review is what FFRR stands for. We start ground testing as soon as the airplane is assembled, prior to paint, and actually as soon as critical systems are integrated. It wasn't even fully assembled when we started making sure stuff worked. This is a kind of a loud video. I'm going to skip over it, but it's basically as soon as the airplane reached this state, we did all of that stuff on the left. We tested our flight control cables. We tested the motor. We had to make modifications to the software and the avionics to trick it into realizing it's okay to have only one engine because it was designed for a twin engine airplane. And we actually started taxiing it around a little bit, make sure the nose wheel mechanism was working. Rudimentary proof limit load tests. Weights and sandbags.
The sandbags buffer, but we're actually adding plates of steel to put the load on the tail. Yep. Much easier than making a wiffle tree with frames and all that stuff. And it passed with flying colors. We were very happy.
I love the group shot after this. 4,800 pounds, amazing. All right. Now, my role was flight testing, and so I joined. Well, I joined during the ground test period, and spent a lot of time on site through flight tests. Had a chance to open the envelope with the chief pilot, Terry Tomini, who spent a lot of time on the design too with Mark and team. But we opened the envelope with 5 flights, single pilot, and then the rest of the flights, the flight test engineer, my role, I was flying right seat with Terry. So I had a really great opportunity to think through how we help each other as we expand the envelope and ensure the airplane's ready.
And at that phase of the program, Terry Tomini, our test pilot, and Ramy, they were actually running everything. So they were overseeing all of the work that we did to validate these the tests. We had to find a big muscly guy to put 300 pounds of push on the side stick. And we were doing all those very rudimentary things. We were hanging weights from the control surfaces. We were doing all sorts of that stuff. But every one of those steps, that entire process, Terry and Ramy put together, and they'd only discovered the airplane existed, a week or two before they flew out, and they were suddenly assigned to the project. So,
yeah, what a day that was. I mean, if you haven't had a chance to experience a first flight of a product that you spent a lot of time on, it's almost impossible not to get emotional. Like the first time it does what you intend it to do is such a rewarding feeling that it's hard to describe. I mean, for those of you on the call that have had a chance to experience that, you know what I'm talking about. But for others, that GoAERO might be your chance to feel it for the first time. It's wild. It's wild. Bucket list stuff. If you like this, if you like building things, it's hard to beat. So our objectives during the test program was demonstrate that the airplane is airworthy, get, of course, the ticket that we need from the FAA to fly in an air show, clear the ferry flight envelope we had to get from Virginia to Wisconsin, and get a minimum of 20 hours on the airframe. Actually, 10 was the minimum. We overshot that, obviously.
I got to ride, I think it was flight 6, where we were going to do the flutter envelope.
Yeah.
So we go up and we get on condition, and then the pilot takes his fist and punches a controller, kicks the rudder, and we want to make sure that everything damps out after that is done. So we do that, have some very, very formal program. And then he said, watch this, Mark. He banked the airplane, pulled back, you got the throttle trimmed, you got the pitch trimmed, he took his hands off the wheels. There we were in a steady 3.5 G horizontal orbit. He said, I can't do that in the F-16 I fly.
Yeah.
But we could do this. Yeah, it was really cool.
We used to have a competition. Obviously, Terry would always win, but it had such a glide ratio that we would cut the throttle. We would see who can cut the throttle and not touch it to landing furthest back, starting at about 20,000 feet. So we flew 19 sorties in Wallops. We got our test conditions done. Just a phenomenal flight test program. A few discoveries along the way, overcame those together. And this is where like everything comes together, and the whole team is extremely engaged. You fly, everyone's immediately reviewing the data. What's working, what's not, what do we need to tweak for the next flight? And just it goes so fast, and it was riveting. Oh, we got to the point where we were so comfortable with the airplane that we safely expanded some light aerobatics. With the FAA, we were certified to do light aerobatics and on the experimental ticket for the air show. So here's what we ended up getting to. As slow as 1.1 stall speed, up to 250 knots, 25,000 feet, and just like Mark said, 3.5 Gs. And so here's the flutter analysis you're talking about. I'm going to go by fast so that we can have a little time for Q&A. One of my favorite experiences was taking the airplane to Oshkosh and trying to be covert about it and having conversations with air traffic control along the way, or landing at FBOs, and people, what is that? And we were like, oh, we can't tell you. Like putting duct tape over our Eclipse badges, and my animation got screwed up there, but pretty fun. So oops, there's a little bit of a slideshow on this one. Here we are at Oshkosh. Made an immense splash. I mean, mission accomplished in the sense of getting the public feedback. It was wild. This is Terry doing a whifferdale at Oshkosh, so like 90-degree bank there. Some key lessons learned here on how to do something like this. I'm just going to put them all up on the screen, and we could. Obviously, if you haven't kind of gotten the hint here from Mark and I, efficient and safe development test, leveraging how fast you can work with a small team. I remember every day having an all-team meeting, and it was like 15 people, 20 people in a single conference room. How many days do we have left? How many dollars do we have left? And whoever said they were going to do a thing, it was never second guessed. There weren't like a bunch of people trying to track. It was just, I'm committing to a thing, and my team trusts me. I'm going to get that thing done, and I'm going to follow through, or I'll let them know I can't. And that level of trust at the individual level was there across the entire team. That's how you can go fast with confidence. Getting some other eyes on it for first flight readiness review was really helpful. Kind of gave us a perspective of eyes looking in. Hey, you might check that. Go do that. That peer review was super helpful. And then we just had a ton of fun. That was any words of wisdom here, Mark, that you want to?
Well, it was. I agree with you completely. It was a once in a lifetime thing. It was top secret. No one knew it existed until during a press briefing in a tent that we were giving on a new project we're thinking about. That is the royal we, Eclipse. I think Peg Bilson was giving the talk, and all of a sudden we hear turbine whine. And the turbine whine gets louder and louder and louder, and then they drop one entire wall, fabric wall, of this thing, and there's a jet, with a fire-breathing jet, and then they power it down, and rock stars pop out. It was Terry Tomney, the pilot, and I'm trying to remember who the second person was.
Vern. It was Vern Rayburn.
It was Vern Rayburn. That's right.
The CEO.
So the press went insane. Where did this airplane come from? So it was really fun.
Super fun. All right. I think we have time for a few questions. Gwen, how you feeling?
I think we're doing all right. So Ramy, I have a few questions for you. The first one is, how many of these aircraft are flying today?
Just this one. The company, Eclipse Aviation, after this, I had to really focus on production. Eclipse ended up delivering somewhere north of 250 airplanes before needing to file I think it was chapter 11. I can't remember chapter 11 or chapter 7, but it was the company had to restructure. And ever since then, the company's been focused on the Eclipse 500, 550, and there may be a subsequent iteration of the very light jet, but this concept never went beyond concept.
Yeah,
this airplane still exists in a hangar in Albuquerque.
The morning that we were going to take orders for the airplane, because a lot of people they were expecting 400 orders at Oshkosh, and we were all lined up outside, ready to go into the new Eclipse hangar space at the Oshkosh Air Show, where people could sign up and get in line for their airplanes, and everyone starts pulling out their Blackberries and their phones and looking at them. And it was announced that there was a takeover, that there was a bankruptcy acquisition, some fellow from Austria. And they said in that announcement that be totally focused on the Eclipse 500, the T-tail twin engine. That was awesome. And that they're not going to do the Eclipse 400, but we'll consider it. And so it was auspicious, to say the least.
What is the single most important piece of advice you can give teams when developing a new craft on a tight budget and timeline?
From building the hardware part, I'll speak to that. Ramy can speak better to the flight systems. To the hardware part, what this airplane was actually designed for 12 critical load cases. So we had experience with airplanes. We knew that the max G pull-up was going to be one thing, the abrupt pitch maneuvers. So all these things that are in the federal aviation regulations, these crazy maneuvers you have to survive. We knew which ones were always critical and everything else was not critical. So that's all we analyzed. And at least through the design phase. And then towards the back, we checked other requirements as well. So there's that, but then parallelizing the work. I remember watching people in Little League Baseball, right? And sometimes you got a star pitcher and everyone else is standing watching him. They're not throwing the ball to each other. If everybody isn't doing something, you got to change what you've asked them to do. Everybody should be actually working to the utmost at the same time. And that means you have to think about what you can pull forward. And what else would you add, Ramy?
From my perspective, two things come to mind in terms of simplifying the advice. Create a plan, not a 10,000 line integrated master schedule. Create a plan, because at 10,000 line master schedule, people get distracted in the details, and that's how you end up going down maybe rabbit holes you don't need to. So a plan helps you constantly think and reevaluate. And to be able to do that really effectively, my second piece of advice is test as early as possible. Test whatever it is, the idea you have, as early as possible. You don't wait till the very end to do all the systems coming together and test, because oftentimes integration is the hardest part. So test the component, test the subsystem, test things as they come together, as you design them, prototype, get that integration at the lower level done first, and then it gets easier as you expand out. So make a plan, not a 10,000 line IMS, and test as early as possible. That's how I.
Amen, brother.
If you were to build a GoAERO aircraft, what type of people, experts, specialties would you want to have on your team?
So from my perspective, if you're familiar with the Innovator's Dilemma book and the author of the book, he did a lot of study and found out that success comes from having done it before 3 or 4 times. Now, there'll be some colleges that are working on this and won't have that luxury. So find anything that's close and relevant. People who build furniture, they're going to be great as fabricators. People who there's all kinds of ways you can find something that you could have people contribute where they're actually using their skill, even if it wasn't on an airplane. And then for me, to amplify Ramy's comment, I kid you not, working on some Navy projects, we just took some flat sheet balsa airplanes that we made a profile of the airplane, a top view of the airplane. So in front, it was an X or a cross. We put the wings on, the tails on, the nacelles on, found out where the balance point was, and gall darn it, if that wasn't plenty good enough to make sure it was stable, make sure that it didn't amplify, and just basic stuff is actually very valuable. You'll be surprised. And make a subscale RC model that's not the real thing, but lets you exercise and try things. way worth it.
Yeah, I got nothing to add to that, Mark.
Anything to add, Ramy?
Nope.
All right. Uh, as this is a manned aircraft, how different would the process be for an autonomous aircraft?
Ooh.
It'll be, yeah, certainly it'll be simpler. The crew station and all those accommodations are complex, but in this case, right, we didn't have to figure out the autopilot like they did, like the Eclipse engineers did for the 500. We got the benefit of a basic inner and outer loop that was close enough to work. You know, it was adequate. So I'm trying to think what else would be.
Yeah, I would say that in the design phase, there will be a lot more time spent in software and algorithm development for how you control the aircraft's navigation, how it senses, like instead of human eyeballs and human hands and feet making inputs, how the airplane itself will sense hazards and make decisions to avoid them. That requires a lot of math and some software acumen. Maybe if you use MATLAB or Simulink, some modeling. So I think the biggest change, like Mark said, it's easier from a safety management perspective. You just got to make sure you can take a little bit more risk. You just got to make sure that the airplane doesn't potentially harm people on the ground. But it does get a little bit more complicated in the algorithm development. Now, with any airplane development, if you have high energy, whether it's electrical systems or whatever, building the aircraft itself can be very dangerous. So you have to your safety management system in the manufacturing fabrication process for you and your teams has to be on point just to keep your teams safe through the build process. Just a side note on that.
Speaking of building in stage 2, the prototype stage, we can build a full or subscale. Would you choose one over the other, and why?
So I've had that question many times before and had the opportunity to test that thesis before. If you think about it, when you think about the types of brains you need to figure out structures, flight mechanics, basic performance, stability, and all those things, it's strange that big airplanes and small airplanes need a similar number. It's not really similar, but it doesn't scale with the weight. If I have an airplane that weighs 10 times as much in our world with manned aircraft, I have way more than 10 times the engineers on that airplane. But in total cost and labor hours, it's dead linear with gross weight, dead linear. So if you make a half scale model, and if you're familiar with dynamic scaling, and we can send you information on that, if you want to make a scale model that does everything just like the real airplane, when you scale it down, let's say it's half scale, then it should weigh 1/2 times 1/2 times 1/2, because that's volume. And so it'll be an eighth the weight of the real one. And if the airspeed will be the square root of a half times this. Anyway, there's all these relationships, but they all tell you that you can learn a ton with dynamic scaling, and it can be at a subscale. At some point, if you got a wing and the Reynolds number is getting low, if any of you know about Reynolds numbers, you do lose some fidelity. But building it at scale instead of full scale, strangely enough, it actually goes almost straight line with gross weight. How much work?
Yeah, I'll pile on there, Mark. I'm a believer, like I said, the two most, from my perspective, important pieces of advice I could offer is one of them was test as early as possible. And a subscale, especially in the context of an autonomous platform or a vertical takeoff and landing platform, a subscale model provides so much opportunity for learning at a lower cost, and you can get there faster. Now, one might think, oh my gosh, I'm going to dump all this money and energy into a small thing and then have to redo it for the big thing. and it's going to cost me a whole bunch more. But I think oftentimes people find that learning and discovering design flaws on the big thing and having to redesign that ends up costing much more than the small scale would have cost.
Yeah.
So I'm a believer in building up and testing as early as possible, learning as much as you can with the means you have as early as possible is really, really good practice. That's my opinion.
The signature of a team that's going to be competitive is a team that flies something first. Find a way to make it dumb enough that you can learn something with the scale model, even if it's hand flown radio control style and there's no autopilot, whatever,
Amen.
even if it's balsa, whatever. Get something flying soon. And if
Amen.
your thing is a little bit like a DJI Phantom, okay, cobble together something, 3D print some stuff, glue it on, and go start exercising. You'll learn so much.
Last question. For the final fly off, we can fly all 3 missions or just 1 or 2. How would you build for that? And how would you make decisions on adversity, maneuverability, and productivity missions?
So Ramy and Gwen are the experts on the mission. I will say that when we've done these types of things, Ramy, I don't remember if you did this in college, but the design, build, fly competition that AAA sponsors, you always go crazy. You're trying to optimize everything. You really are. And optimization is so cool. I always get suckered into it. But actual functionality, you can't go to the party if it doesn't have basic functionality. And basic functionality and basic capability always wins. And I hate that because I want the optimum, the one that was mathematically optimum to win.
Yeah.
But truth is, reducing it to practice, that's how you win. Actually making it and showing it, regardless of what the beautiful ISO plot of optimum this or that. You got to do it. It's going to be good. It's going to give you that direction. But you'll have to walk away from that real quickly, get down to reducing it to practice so you can fly readily.
Yeah, I suspect that the decision on, which missions to fly, 1, 2, or 3, that decision will come later in the game. And once you get to know your product a bit, I think you start by seeing what does the mission need, what skills does your team have, or what skills are you going to acquire, lean into what you do well. So lean into what you do well and get those technologies or that capability validated early, and let that guide you in how you shape your approach to the competition. Because like Mark said, if you end up trying to do everything, knowing that you have gaps, and then you start to de-optimize or sacrifice what you do well in order to do something that's completely out of your swim lane, you might end up jeopardizing the whole thing. So, having those trades as a team and making some of those difficult decisions is really part of the journey. And Mark and I tried to give examples of some of that as we were going through this story, where, we went higher on safety factors so that we wouldn't have to redesign parts that we knew had risk. We had to do tests earlier than the airplane was ready, to know if we're headed down the right path. And then we had to take some really calculated risks, like locking down the outer mold line without the structure. We had to use some judgment. Luckily, we had a team that is like Mark and his team that had the experience to be able to say, I have confidence we can build a structure to this outer mold line. I don't have strange aerodynamic features that are going to require some miracle. So I'm using judgment to make that decision early. And as you build that out in your project, whatever you lean into will help shape how you approach the competition the closer you get to it. So I don't have like go do this over that, because it's going to be different for everybody.
All right. Well, thank you both so much for joining us today. And thank you everyone who joined us for this expert lecture. We will be having another expert lecture next week, and we look forward to seeing everyone there again. You can catch this expert lecture and all of our expert lectures at herox.com/expert lectures. So we will see you there. Have a great day, everyone.
I
Good
just
luck,
want to
everybody.
say thank you, Mark. Thank you, Ramy, for a phenomenal lecture. Truly appreciate it. And to everybody, the lecture that we have next week is with the FAA, and we'll speak about your pathways to be able to fly. So that is very important as well. So with today, you learned how to make it happen quickly and safely. And next week, you'll learn the ins and outs of being able to fly within the regulatory framework. So thank you, Mark. Thank you, Ramy. Thank you, Rebecca, for helping. And look forward to seeing you all at our next expert lecture. Take care.